Mm-hmm.
Yes. And we should prove this HR type independent of choice of this invariant by symmetrical bilinear form. And since we have
so we need to, okay, yes. So as you said, if we choose another form, then it will be the same. Okay.
Yes.
Mm-hmm.
And I mean, for semi-simple algebra, G have the decomposition.
Mm-hmm.
I mean, the rule system. And this is the Cartan algebra.
Okay.
And for any such invariant bilinear form defined on this list, we can see that we can find some E and F E.
Mm-hmm.
Such that
this is for every E and F from G alpha and G negative alpha. It's not like you can find.
Yes.
Yeah, I mean, of course you can find them, but they all this with this property. Yes. Uh-huh.
And then we can also make this.
You can, yes, you can find such that. Yes.
This,
Okay.
This we have.
Mm-hmm.
And these things doesn't depend on the choice of the product.
Why?
I think that is the lead bracket.
But you just said that let us. No, what does it mean? These things. So E and F, as you introduce them, they do depend on the form, right?
So, but for any alpha,
Yes.
is the dimension of G alpha is 1.
Yes. But you need E and F to be like that. So how do we choose them? So you have form here, right?
So you here E and F depend on choice.
Yeah. Well, maybe they don't. I don't know, but you need to. But in your definition of E and F, right, you would like to scale them according to something, right? And this something includes form inside. So far it's not clear if they depend or don't depend. As it's yeah.
Or maybe this is okay. I don't know.
Okay. So hint. Yeah.
Is that the decomposition is not independent on the bilinear form?
This decomposition is does not depend on bilinear
Then
form.
if we have this, the final equation, I think, because the lead bracket and the E and F are all the things not depend on the.
Why E and F do not depend?
Because E and F from the independent decomposition.
Okay, so let me take E from here and F from here. But you need to choose E and F somehow, right? And this choice is given by this formula, right? In this formula, you have bilinear form in two places. So if you're saying that it does not depend on bilinear form, then you have to prove something. So hint here is maybe try to show that H alpha does not depend on the form for simple algebra. Yes. So for simple algebra, you have only up to constant only one form. Yes. So actually, if G is simple, then if you have form 1, then it is actually just some constant C times form 2, right? But then you have H alpha actually somehow depends on the form, right? Right? It actually says that, well, your H alpha 1 that depending on the form 1. What it is such an element such that this together with some H, right, is alpha of H. This is with form 1, right? And then with form 2, it should be the same, except I should take 2 here, right? And 2 here, yes. But I can erase 2 here, or maybe let me do it like this. Erase 2 here and like this. It means, it means that H alpha 1 is C H alpha 2, right? Okay, so H alpha, did we get, right? So H alpha is 2, well, let's say 1, right? Is 2H alpha 1 over alpha 1, right? So this guy is C, yes, we have CH2 alpha divided by alpha 2, but I need something, right?
We just multiply C.
Yes, I would like to have this one, but this is not good as it is.
No, I mean here. You write 1 here, and this is. Oh.
No, so far it's not. We have some mistakes somewhere, right? So let's try to do it again. So suppose I have this, right? So 2 expressed in 1 like this.
Yes. Since we have these, if there is C,
bracket
and
is
if you change the position of C, this is 1 over.
No. I would like. Yes. C is here. Yes, this is the mistake. Thank you very much. And therefore, I have 1 over C here, right? And 1 over C here then. So H2 here, right? So H1, right, is 1 over C H2. And 1 over C here. So this is H2H alpha 2 over alpha 2. So this is H small alpha 2. Yes, very good. So this is for G simple. So how for semi-simple?
We should change this equation to be some sum of the.
Yes.
Take a semisimple and decompose in simple.
Mm-hmm.
Add some in this.
Right, so my H alpha, so I take H alpha, right? So the question is that really, what all my constructions, do they respect this decomposition of simple, semi-simple to simples, right? For example, Cartan subalgebra.
Like if the Cartan subalgebra of the semisimple is small Cartan subalgebras, and then
Yeah, so it's actually right. So you need to show that. Suppose that G is semi-simple, right? Then and H is Cartan subalgebra. Then I would and G is then G1 plus and so on plus G K, where GI is simple, right?
you want to prove that the projection is also.
Yes. So so we have projections. So pi k pi I, right, is a projection of G to GI, right? So I would like to see that actually my H is the direct sum of pi I of H's, right? Which is kind of clear, right? This is Gothic H, right? And then that pi I of H is Cartan in GI. Yes. So if we check this, then this also we need to check this. So checks to be made. And then also you need to check that your invariant bilinear form on G actually restricted to GI is also invariant bilinear, non-degenerate invariant bilinear form, right? So this restricted to GI is non-degenerate invariant bilinear form. Right. So then what we did, all computations that we did here can be just made on each term here, right? And so you take your H, some element, consider its projections. All these projections, they don't depend on your form, right? But for the same reasons here. And therefore, the whole thing, your element also does not depend on the form because it's a sum of them. Okay. I don't know. Should we check something or just proceed to the next problems? It's not the most interesting. I think it's interesting to draw pictures. Yeah. So this is the idea. This is the checks to be made, right? And the most crucial computation we did. Okay. Very well. So let's proceed then to okay. So what was doesn't depend, and also we need to check that H alpha span Cartan subalgebra. Yes. So let's C. So proof actually by contradiction. Okay, I think, yeah, I understand that it was not too much time, so today I will be helping with this a lot. So so next statement is H alpha, as alpha is in R, span span H. Is it H alpha or alphas? I think it's actually the same statement, right? It's actually the same statement that alpha, right? So that R span H star. So we kind of proved that last time, because.
Can I say something?
Yes, sure.
Because for me, I don't know if what I'm going to say is correct.
No, that's the seminar, so you can say it here.
For me, it was more or less obvious because we said the last class that we have the isomorphism between H and H star. Because we have a non-degenerate bilinear form.
Yes.
So
This one is clear. Yes, because again, this is an isomorphism. So from alpha to H alpha, you still, if you have linear dependence on alphas, right, then you have linear dependence on H capital alphas, right? And this is the isomorphism that we introduced. But H small, they are just some H capital alphas rescaled. So still we have some linear dependence. So this is clear, right? But why R span H star? This is almost clear after we proved. So we proved that if I take R and consider its real span, it will be positive. So then the form will be positive definite, right? But then if I take so on here my form is positive definite, and therefore on here my form is negative definite, right? Because then you have I square like everywhere. And then it just means that this actually this is actually H star. So it's related to the positive and negative definiteness of our form. But you can prove it. I'm just trying to relate it to lectures. I'm not saying that it is this like a proof. I'm just saying that it is related to what we said on today's lecture and in the end of the previous one. But you can just see it directly. So let's prove this one. How to do this? Well, so suppose not true. So assume not, then it means that so suppose I have some basis, right? So suppose I am taking right. So how to say it better? Right. So I would like to say that then there is some element then there exists some element h from h such that alpha of h is equals to yes, okay, alpha of h equals to 0 for every alpha from R. So how do I check this? So assume not, then let me take take my span of roots, right? This will be some subspace of H star, right? I don't know, let me denote it HR is actually span R. But in this case, it's complex span, right? So this is just notation. And then HR is a so if not, then it is a proper subset of H. Sorry, H star, right? All right. It's unfortunate notation because, I don't know, it's not both R from the lectures, it's just I take R and see what the subspace I have, right? If R spans H star, then it's the whole, then this subspace is the whole H star. If not, then it's just some proper subspace. Right, and then I would like to introduce some basis again, which is like the first k elements is the basis in here, and the rest just completion of to the basis of H star, right? So I have lambda 1, lambda n basis in H star such that the first k elements is a basis in H star R. Okay. Then let me introduce. So let V1 Vn be dual basis in H. Right? So I have Vi, so lambda I acting on Vj is just delta Ij, right? So if HR is not the whole thing, therefore k is less than n, right? So let me take Vk plus 1. Right? So all lambda i's acting on Vk plus 1 is 0. Right? For I from 1 to k, just because of the basis that I chose. Right? So no index k plus 1 here, so therefore they all miss Vk plus 1. But so therefore, but lambda 1, lambda k is a basis in here. So therefore, all roots they are linear combinations of lambdas from lambda 1 to lambda k. So therefore, for all roots, we have alpha of Vk plus 1 is 0 for all roots. So my Vk plus 1 is that H that I'm looking for. But you see, so alpha of H is 0 for any root, right? It just means that add adjoint action, so it means, so this, so yeah, so my H, So I claim now that my at h is 0. Why is that? So it's just because, remember this, that G is H plus direct sum of G alphas, right? So whatever element I choose here, if I commute with H, I will get like something like alpha of H times this element. But alpha of H is 0 for any root, right? So therefore, adjoint image of the adjoint is 0. But that means just that H is from the center. But my algebra is semisimple, so therefore H is 0. Right, so H is so H is from the center, therefore H is 0. Right, why did we need the H is 0? No, H is, yes, so there exists, so our assumption is that there exists non-zero H, right? So if my alpha does not span, right, that was one element of a basis, right? So it's not like H is 0, it's a contradiction to this to be dual basis, because we chose Vk plus 1 to be not 0, of course, right? Contradiction. Yeah, so that's how you prove that it's actually spans. All right.
First, we assume that our semisimple algebra has a decomposition.
Decomposition.
Something G I G minus I. And we analyze the dimension and the number of these i's. So if we assume that dimension of this guy is maybe if it is n, then by this property and the number of alpha should greater or equal than n.
Okay, so what's written? It's what is curly braces?
Okay.
Sure. Yes.
Yes, and
Even maybe twice of that.
yeah, you mean twice is the dimension of this part, but I mean just the number of alpha, which I will take some here. So the dimension of G.
The dimension of H. Okay.
Should greater than, so first this part n plus this part 2n.
Okay. Yes. Yes.
Okay, I have a question. Why isn't that the number of alpha is greater than the dimension of h? I can think of examples.
Because the root system span this,
Yes.
and the dimension of h star is the dimension of h, and the span means maybe there is not a basis, just maybe we have a more vector than the dimensions. So at this moment we can see that because we are analyzed about dimension of G should be 4, 5, 7. So at this moment we should see that n should not greater than 3. So n can only
Yes.
be 1 or 2.
Yes.
And for the case n is 1, it means this guy is 3-dimensional.
Why?
No, 3. It's just when it's 1.
Yes.
This is 1,
Yes.
and it should be 4, 2, 4, 6, or something. But the sum of this dimension will not give us.
Right. So it's even at least. At least it's odd, right? So it cannot be 4.
Yeah. It must be 4.
No, I mean by what you wrote here. So the dimension of this is even. So the dimension of G is odd, right? So we ruled out this.
Yes. And about if the dimension of this be
Now, yes. So if it's 1, then it's not 4, right?
It's not 4, yes.
But
It can be 2.
It can be 2, and then
no. But if it's 1, maybe we can rule out everything.
yes. This is the sum of 1, 2, and 1 are not connected with all these things.
Okay.
But
That's a why? Why?
Can you explain?
yeah, but we have 6. Maybe 4, 5, 7. If the dimension is 1 here, it means
This just means that you have just 1 alpha.
1 alpha. Yes.
But why?
Okay. So why?
Because the
Good question. Yes.
the semisimple algebra coincide with the root system of this is coincide with the reducible abstract root system, and for that, if alpha is C beta, C must be so we have only one.
The thing, yeah. So the thing is maybe, so you have H alpha. It spans H, right? So it means that if you have two roots, alpha and beta, I mean, which are not, which are different and not alpha. Alpha is not plus minus beta. I mean, okay. I would like to see that H alpha and H beta are not scalar multiple of each other, which is also kind of clear because again we have an isomorphism between H star and H, right?
It's not about also like you will have like 2 copies of SL2 alpha and beta, but
But I don't know. Maybe the life is like that. They share the same.
Which case we have discussed?
But I think this is already wrong because the semisimple algebra coincide with the reducible abstract root system. So
Yeah. So what wrong? Nothing is written yet. So
we will
yeah,
not
so-
have another B with this property.
Right. So what I'm saying, if that, suppose that I have alpha, suppose in my G, like I have 2 roots which are linearly independent. Then I claim that H alpha and H beta are linearly independent. Okay, so that's the statement that I'm making, right? So this is clear why, right? Because I have this isomorphism to H capital. So if alpha and beta are linearly independent, then H capitals are linearly independent. But small h's, they are just scalar multiple of big capitals, right? So therefore, if I have, so this means that if I have 2 roots which are linearly independent, then these are linearly independent. Okay, so now, so suppose that n is 1.
Then it must be true.
Yes, then I have just one root, because if I have some other root, I mean one, which is, I'm counting only this part, right? So of course I have negative also as a root. So suppose I have another root which is linearly independent. Then I already will need dimension of h to be 2, right? So if a dimension of h is 1, then I have one root only. And but we know that the dimensions of these things are 1, so it's 1 plus 1 plus 1. Only thing that can happen.
Yeah, so it means we have this.
Yes.
So
if n is 1, we ruled out all of this.
next, if is 2, then this part might be 4. It's already impossible. 4 because it's much greater than 2. 2n, yes.
Yes, 2, 4, it's 6.
Dimension should be within 6. So, only to write 7.
And what? 4 and
Yeah, so we ruled out 4 and 5,
Yes.
like this, right?
yes,
Why cannot it be 7 though?
because if 7, then this is a 5 dimension, but it's impossible. Some odd dimension here.
But then also we cannot have 8 of dimension 8.
Dimension 8, but 8
Yes.
is not included.
No, I mean, but
No.
an solution because for each alpha sub I we have h.
I'm sorry,
sub I.
dimension 8 we can have, and there is SL3 is the dimension
No,
8.
But we're not
why
talking about
it's
dimension
not
8.
like related with this fact that we have to get linearly independent for each alpha sub I.
Yes, okay.
We will have an h sub alpha sub I linearly independent to everything else.
So right. So this is applicable when we talk about like 2 roots. If we have three roots already, like in SL3, the third root is a sum of the first 2. So the picture we saw this picture in the first semester. So what is the weight diagram of a joint representation? It was like this. So you have multiplicity 1, weights like that, and 2. And in the middle you have multiplicity 2, like the 0 weight, which corresponds to 2 elements in the Cartan subalgebra of SL3. Okay, and your roots are, so this is one root, this is another root, but then you have alpha 1 plus alpha 2. So what I'm saying is that this argument that I'm making still works here because I have 2 linearly independent roots, right? And they give me 2 linearly independent H alphas. Okay, so this is 0 weight subspace. Right. So H is a 0 is exactly 0 weight subspace.
It's because I thought like if we have 3 roots, like
Yes.
so we have like 6 G sub alpha, right? Because it's
Yes, yes.
so we have to have dimension 3 in our subalgebra.
Mm-hmm.
Yeah.
Yes, but so it's not like, so the thing is, if I have 2 roots that they are linearly independent. Then I have in dimension of h to have at least, so to have to be 2, yes. But then if I add another root, like in case of SL3, it's dependent with the first two. It doesn't mean that I have another multiplicity here, right? So h alpha plus beta is actually dependent of h alpha and h alpha 1 and h alpha 2 here. So actually, it's not that simple in this case. But okay, so what? So we have, so if, again, going back, so if n equals 2, right, then this can be 4, right? At least, should be at least 4.
Might be 4 or 6.
So yes, then
This can get
then it will be 6, right? But it can be, so suppose that I have more roots, right? It can be 6, right? 6, 2, it's 8 already. So we kind of skipped this one. Yeah. Yes, okay. Yes. Very well. Yeah, what about 6? Do we have semisimple algebra of dimension 6? SL2 plus SL2, yes. Yes. Very well. So we will need all possible. Right. So the problem, if I remember correctly, right?
We need to find. We have this.
We have this number, right?
We have this, and we need to find the values of the angles.
Yes.
And also this value.
Yeah, all possible. Yes.
And
they are related, right? Phi angles and relative
yeah.
lengths. Yes. Okay.
So we can write and beta as just.
Yes.
So this cuts.
This cancels.
So n alpha beta just becomes like.
Can you also cross out the 2 over there, just to make it? No. This one.
I removed it. Yeah.
No, since you crossed the upper one, just
Okay.
to be consistent.
Yeah. So we have this. Right? And similarly, we can find beta alpha, which will just be
Right.
and the angle is just same. So
Right.
now.
No, not psi, but the same. Phi.
Yeah. I'm sorry. I just write it like that. So. We can take the product of these two, and these will cancel,
Right.
and we'll have and it will just be just 2 into 2, just 4 times cos square. So we have one relation like this,
I agree.
and we need to find this, right? Anyway, so now this actually will have some integer values, right?
And alpha betas are integers, right?
Yeah, because they're integers, so we have the possible values are just 0, 1, 2, and 3. 4 cannot be because you don't need the multiple, right?
Right.
So these are the only possible values, and then we need to take for each possible case the values of this and this, right? And then we need to find first the phi, right? So let's take we start with 0. Okay, so well, for 0 is just pi by 2. Right?
So
Because
if it's 0, then both n alpha beta and
they
beta
are 0.
alpha.
Yeah, because it's just n alpha beta has to be 0, right?
Right.
Because we need to make this product 0. So that means that phi has to be pi by 2.
Yes.
That means that this is 0.
Right.
And we need to find alpha by beta. Alpha by beta can simply come out from.
Well, it can
I
be
think
any.
it can just be. It can be anything. It's
Yes.
alpha is just.
This is the case of reducible root systems. Not reduced, but reducible. It's just a union of two orthogonal root systems. Doesn't really matter. You can rescale them independently. It still will be a root system because reflections work independently.
So this is the only case for 0. Now we need to find possible combinations for when. So we take the first case, and that is like both are 1. First case is this. Now, so if it is 1, and then from this, it's just right, and it's just cos phi is equal to 1 by 4.
So cosine of phi is plus or minus
Plus minus. Yeah.
1/2.
And from this you can just find phi.
No, sure. So phi is what?
I think it is
Pi over 3.
Pi over 3 or 2 pi over 3?
Yes.
I think it's 2 pi over 3, but
Well, both. Pi over 3, 2 pi over 3. It can be.
it can be, right?
Yes.
Okay. So yeah, so that's like
We're interested in angles only from 0 to pi, right? Because
Yes.
you know, otherwise we're just measuring not the
and again we use the
smallest
same
angle
thing
between them.
to
So it's both. Phi is 2 pi over 3 and phi is pi over 3. So what I'm suggesting, so all this is good, and I would like to use this part of the board just to organize that into a table.
okay.
So what you compute, so let us read. I'm taking one. Okay. So what we have, I would suggest, so first of all, let me take alpha to be, assume it's greater or equal than beta. Okay. So in the first column, let me take this n alpha beta times n beta alpha, this value. Then n alpha beta in the second column, n beta alpha, and then phi, and then their ratio. Okay, so far we have 0, right?
Yeah.
And then both of these are zeros. Phi is pi over 2, and here it's any, right? Then suppose it's 1. So what can happen? It can happen that we have 1, 1,
Or minus 1, minus 1.
and minus 1, minus 1, right? So if 1, 1, right, so your phi is either 2 pi over 3 or pi over 3, right? So since your alpha beta is 1, you said, right? So it's positive. So it should be pi over 3. So for positive n alpha beta, right? So n alpha beta, remember, is this one. So this is positive, right? For 2 pi over 3, it should be the negative. So you have pi over 3 here. And what's the ratio that we should compute? What should we put here?
We know n alpha beta, which is
Yes.
just 1 square root over 1.
Yes.
And we know 2, etc. And cos phi we know from there, it's just 2. So alpha by beta should be 1 by 2. No.
So cosine, what is cosine? Is 1/2, you say?
Yeah, it's 1/2.
Yes. So alpha to beta is 1.
Yeah, alpha to beta is 1.
Very well. So here, since I take negative 1, right, this is negative,
Yeah, yeah.
so I should choose 2 pi over 3. And this is again 1.
Yeah.
Okay, so let's proceed. Now I guess we should choose 2, right?
So it's just 1, 2 or 2, 1 and
Yeah, so for 2
I think
we
it's just
we
the
still
same
need to compute something, right?
should we compute or?
Yeah, please compute. Here I'm just kind of summarizing what you did here, all your
I
computation.
actually wrote everything, but should I just write the result or?
No, just compute, okay. So if n alpha beta and beta alpha is 2, so next case.
Okay, so we have n alpha beta is supposed to take 2, and then beta alpha is equal to 1.
Right, it can be either 2, 1 or 1, 2. But okay,
it's the same thing.
let us see that we assume that alpha is greater than beta,
Yeah.
right? It means that n alpha beta should be greater or less than n beta alpha. Let us see. So I think n alpha beta is greater because here we have alpha in numerator, right? So therefore, it's either 2, 1 or negative 2, negative 1.
Yeah.
Okay, so right. So what's the angle then? How to compute it?
We know this again.
Mm-hmm. Oh, okay.
Oh no, we don't need it.
Well, you need this for ratio, but whatever.
Yeah,
Okay.
first I need to calculate it.
Yes. Okay. Yes. Right. So you're using what, this boxed formula, right?
Yeah, yeah. This
So this is 2 over 4 is cosine square.
yeah, yeah.
Therefore, cosine is 1 over square root of 2.
Yeah, yeah.
Well, since our angles is from 0 to pi, we don't need to write plus minus there. So cosine is positive. So therefore, phi is what?
It's just 45, pi by 4.
It's either pi over 4 or 3 pi over 4, right?
Yes. Yeah.
So one of these values goes here and the other one goes here. So we need to choose which one goes where.
And so.
Okay, present. So what should I write here?
I think you should write 3 pi by 4.
let's see. So if I choose, so here my n alpha beta is positive.
Yes.
So if my angle is obtuse,
Mm-hmm.
then this thing is negative, actually, right?
Yeah.
Because projection will be on the other side of the continuation, right? So here I should have pi over 4, and here 3 pi over 4. Okay, what's here? And so let's compute it.
Wait. We have
Right, 2 is n alpha beta.
and we have 1 by root 2.
2 times the ratio. Yes, and times 2, because we have another 2 here, right? So square root of 2. In both cases.
In both cases, yes. Then
And
we
3.
have another case, like 3.
So in 3 again we have 3, 1 and negative 3, 1. Negative 3, negative 1.
And we again do this. So,
Okay, so let's compute.
so we have
What is the, what's the angle? Yes.
3 times 1. Yeah, actually I wrote it, so and there will be 2 cases like
Yeah, so cosine is what? Square root of 3 over 2. Yes.
so there will be one is 5 by 6
Mm-hmm.
and another is
5 pi over 6. So pi minus pi over 6. Yes.
So from again we try to see for which one is negative.
Yes.
for
So
the-
negative
for
should
this
be.
one, it should be pi over 6, and for this it will be
Yes. Okay. So obtuse angle for negative
5 pi over.
and acute angle for positive.
Yeah. And
And
again
here?
we just plug this in for the first case. It's just
Yes. So
3,
this is 3.
3.
Yes. 2 times square root of 3 over 2.
Yes. So it's 3.
Mm-hmm.
And it will be simple.
Yes. Square root of 3, it's square root of 3.
Okay.
Okay. Very good. So now we should, yeah, thank you very much. Now we have all the information about rank 2 systems written actually on this book, in this table, right? So now we just need to use this information and draw pictures.
Sorry, a question. Why cannot be 4, this thing?
So if,
It is, we decided that it's not a multiple. Of
yeah, so if this is 4, then this is 1. Then cosine is 1, it means that phi
it's the same.
is pi. So, right? And so if phi is,
No, it's 0.
Because these are not numbers, these are vectors.
No, when it's 1, it's
1 or negative 1, right? It's a cosine square here, right? If it's 1, then again it's just 0 to pi. It's just the same root. if it's negative 1, it's just negative of this root. So we assume that beta is not plus or minus alpha.
So it cannot be there. Okay.
Okay, so we had two parallel explanations. I hope that both of them were useful. Okay. Okay, Abner, can you show us any root systems of rank of R1?
So we want to, for a system root, after abstract system root in R1, the subset that generates, in order to check each property, it's how I construct it. So first we want to span, so any number in R1 spans R1, because you only have to multiply for any other number. Okay,
Sure.
so it just has to be different from 0, so I just take R1. Okay. Well,
Just any vector? Okay.
yeah, so it also has to, yeah, we have two of them. We have to what the inner product here is just product. So okay, yeah, it has to be in Z. It has to be an integer. But it is the same as just. Alpha. So if this has to be the same as name, and this you have that beta has to be alpha. So we can fix the alpha and get all the other numbers through this rule. And well, it also has to be that is alpha to beta. It's again this again. It should disappear because yeah, at the end we will have just minus beta. But if we just choose a negative m, we will get minus beta.
Why this was in the bottom disappeared? Some magic.
Because here I didn't write what was this exactly.
Okay.
Okay.
We can help you. It was
Yeah,
minus 2
yeah,
alpha
minus
beta
2
over alpha alpha.
Beta. And I think it's beta in this case. No. It's
Alpha,
again
alpha.
Yeah. Alpha. Alpha. So it's again product just. So this goes on this. We get
Wait. What's happening? So you cannot cancel vector with.
well, it's R1 just numbers. So this is just product.
Okay.
Yeah, sorry.
Wow.
And okay, so we only say that if we have two of them, we have to have also the negative of each one. So we also have to check which alpha also holds this equation. And if we want that, because if we want also to have beta as minus alpha, and we only have need anyone just to choose minus 2, we will get minus alpha. So minus alpha is again in our system. Okay, now we will describe how it looks. It's just R. Well, maybe we can index as alpha, with alpha in R1 without 0. And will be, guys, it looks like this. all equations.
So what if I take m equals to 5? Right?
You will get 5 over 2. No, you have to choose also alpha.
Okay, so suppose
Okay, yeah,
alpha.
it would be
Suppose
just-
alpha is chosen.
Uh-huh.
Yeah, so you have. You're saying that you will have root 5 over 2 alpha. I think that something bad can happen because then so you have alpha and 5 over 2 alpha. Or even let me take m to be 6. It's actually not to write these fractions.
Okay.
It will be alpha and 3 alpha. Try to compute. So this is beta, right? So if you try to compute n alpha beta in this case, try to compute.
But you already choose this one again.
Yes. So suppose alpha is this one. Suppose beta is this one.
But I didn't. It looks.
And
like this.
these are two elements of your root
But
system.
that's when m it's m equals to 6.
Okay, that's okay. So you're claiming that you have a root system with such two roots, right? So I'm asking, can you please compute an alpha beta for me?
Yeah.
For such alpha and beta? I'm sorry, at the bottom you should have beta beta. I mean, it depends on notation, but in our lectures I had a beta beta. Okay. Yeah, so just erase that. You cannot.
Yeah. Okay.
Yes. Okay. Yes, you can do this. Sure.
Okay.
So you have 2 over 3, which is
So maybe-
something bad.
Okay. Maybe it would be changed in this case. Maybe it would be. No, maybe it's also.
So this example actually shows that you cannot have, if you have alpha in your root system, then you cannot have 3 alpha already,
Yes.
right?
Yeah.
In any root system that you chose, like only multiple of alpha that can happen, just 2, or negative alpha. So this is the same computation that we did today on the lecture. That alpha, so suppose you have 2 roots, alpha and c beta, and c alpha. Then we had that c is actually from this set plus minus 1, plus minus 1/2, plus minus 2.
No, it cannot be 2. Yeah.
Well, it cannot be 2 for reduced. We never said that we are looking for reduced ones.
Okay.
So actually what happens is that once you've chosen alpha, of course you're right, you should have negative alpha as well. So for example, this one is a root system in R1, right? Also you can choose alpha and then 2 alpha. And then you should have negative alpha and negative 2 alpha. This is also root system, right? And you reflect, you get also root, and when you project another root, you get integer. Okay? But then this is it. So this is we have two possible up to rescaling root systems in R1, which are these two.
Okay, yeah. So it would be, instead of m over 2, just that number.
So here, yes, not m does not run over z, but over small set.
Yeah.
Yeah. Okay, so who? So reduced of rank 2 then. Yeah, just draw a picture, right?
By using this thing.
Yes, yes. Okay, so maybe I can draw pictures, but it still needs some argument, right? So okay, so number 4. Okay, I have a honor to draw pictures. So these pictures, that what you should remember and think about all the time that we're working with root systems. So how to classify all root systems of rank 2? The recipe is the following: take 2 roots, which are not collinear, but the angle between them is the maximal. Is maximal possible. Okay. So. And angle is maximal.
So, is this the rule to a picture or just
What?
another argument?
No, this is an argument. So how to check that I draw everything, right? So I should start with some roots, right? So of course I'm taking 2 roots and they should satisfy something from this table. So to not making like the same picture by different choices, I would like to choose alpha and beta such that in my root system, angle between them is maximal. This means that I am choosing simple roots, but it's just like easy way to formulate it for rank 2 systems. Then what can happen? Well, so we are just going over. So if this angle is smaller than pi over 2, then I can take reflection of S alpha of beta and take angle greater than pi over 2. Right, so I'm looking at angles which is greater than pi over 2 here, or equal to, right? So if it's exactly pi over 2, then my root system is like that. And that's it. Well, so this is just what's called A1. For some reason, we would like to call this root system A1 by A1 joined with A1. Because this is A1 for some reason. Okay, we'll see why in the future, maybe today. So we will have it A2 at least today. So, all right, index for A corresponds to the same index as ln has. Actually, +1. So A1 corresponds to SL2. So these are 2 roots of SL2. You can, either go by E or by F. Right? So these are this direct sum of SL2s, actually. All right, and this is the only thing that you can do if phi is pi over 2. Because suppose that you can you give me some other root, right? Suppose that I didn't draw all the roots that I can have in this root system. Well, it cannot be here because then the angle between these two is not maximal. If it's here, then I reflect with respect to alpha 1 and get angle greater than pi over 2. Right? So no roots here or here I can have, because otherwise it contradicts to alpha beta being 2 roots with maximal angle. So if angle between them is pi over 2, then my root system is like that, and this is my root system. Like first one, the simplest one of rank 2. Okay, phi is 2 pi over 3. Okay, this is something more interesting. So 2 pi over 3, I should draw equilateral triangles. And this picture should be familiar also to you. I think I even attempted to draw something like this in the seminar today. So 2 pi over 3. So my first root will be this one, and then another root is this one. So alpha beta is like that. So this is 2 pi over 3. But then I start reflecting. If I reflect this one, this becomes this one. And then by reflections, I will get all this. So this is alpha plus beta, actually. This is negative alpha minus beta. This is minus alpha, this is minus beta. So this is already some root system.
Alpha plus beta over 2.
No, this is exactly alpha plus beta. Yes. So this is some root system. If you check, then this projects to this exactly to 1/2 of the other root, and this happens for every root here, right? So I cannot have any other roots. I did not, for this case, I did not miss any other roots. So suppose I try to draw some root here, then by reflections I can get a root which with angle more than 2 pi over 3, which contradicts for maximality of this angle that I chose in the beginning. So that's the only case that I can have for this, and this is called A2. This is SL3. If you remember these pictures, again, this is a joint representation of SL3, right? Okay. How about phi equals what? 3 pi over 4. Uh, 3 pi over 4. Okay, in this case I should draw a square. And in these squares I will have diagonals and this. So I will have alpha is this one and beta is this one. So first of all, if my angle is like that, then the ratio is square root over 2. It's exactly the ratio between, if this is square, it's exactly the ratio between these two. All right? So that's why I can actually do something like that in the square. So this is alpha, beta. Then I start reflecting. So okay. So then when I start reflecting, this goes to this one. If I reflect with respect to this plane, which is orthogonal to alpha, right? Then I can take this one and reflect with respect to, well, of course I have negative alpha. So to get, I also will have this one. So how to get it? It's reflection of this one with respect to the plane which is orthogonal to beta. Okay, then I get this one. And therefore, I have all these roots. So this is beta plus alpha, and this is beta plus 2 alpha. And you put minuses and get the others. And again, for the same reasoning, so suppose that I can have some other root system with such a choice. Maybe I'm missing some roots. So this is already root system. It's closed under reflections. projection is to half, every root is projects to the other root to half or to the whole root, right?
I think alpha and beta should be.
I never fixed which one is first and which one is the second.
Okay.
That doesn't really matter at this point.
Because
Just the answer is our name.
okay.
Yeah,
Excuse me.
Sure.
Can you please explain again how we have the beta alpha and beta plus 2 alpha through reflections? I can see.
sure, yeah. So we have these two in the beginning. So this one is the reflection of alpha with respect to this plane. And this plane is orthogonal to this root that we have already. Now, to get this one is a reflection of beta with respect to this plane, which is orthogonal to this root. And again, if I try to enforce some more roots in here, then by reflections, I will get a root which is which will have angle with alpha, say, bigger than this one. Okay, so that's it. Oof, and the most hard one to draw. Maybe let me not. Okay, so I covered 0, 1, 2, right? So let me to have more space erase everything, but 3. Yes. Okay, so let me first draw a picture. Then, so it is like that. This in this case, so if phi is 5 pi over 6. By the way, this one is called B2, which is the same as C2 for some reason. And then D2 is the same as A1 joined with A1. You will see why. This all comes in the future. We will have Dinkin diagrams, and they just labeled A, B, C, and D. These are just some graphs. And if you reduce it to lower ends, some of them will coincide. So that's why we have such strange things here. But this is just something that comes from bigger theory. That's why. All right. Okay, this one. So the picture should be like that. I will have two, again, I will have roots of two sorts, long one and short ones. And both of them actually gives me some root subsystem of type A2. So actually it's like that. Easier to draw it like that. And then I find middles of these triangles. And I have a bunch of more roots. Like this. So my alpha and beta are this. Alpha and beta. So the angle between this one and this one is 2 pi over 3. Between this one and this one is 5 pi over 6, right? So I also add 5 pi over 6 to this one. Yes. And I think I drew it in a very bad way. Let me try again. So what I would like to, because this should be on the same line. So these three middles actually. So it's like that. Because this root is this plus this plus this. This I know for sure. Maybe okay. You saw the picture. I just want to make them on the same line. Let me try it again. So I need some equilateral triangles, right? Okay, this one should work better. And then I have this. Actually, they are not in the middles. They are like that. Yes. So I have this. Right. Wait. What? So. Sorry. I think I'm confusing a little bit. So this system is the most tricky one. It's G2, which is exceptional algebra. So that's why I'm struggling a bit. So yes. So let me look at this picture just to remember. This. No. I think yes. I think this is okay. Yes, I was right. So these are still middles. No, I'm correct. Yes. Okay. So I'll tell you why I was confused the first time. So they are not on the same line, sure. The ones that I tried to put on the same line. What is on the same line is this. Yes, okay, that was my confusion. Yes, so this is alpha, beta, and that's how it goes. And this is G2. G2. So you will have E and F, but for E you just have E6, E7, and E8. These are exceptional algebras. And then F is 4. F4 is another exceptional algebra. And then D is classical. One of the classical algebras is SO2N C. Dn, so you have series Dn.
Is there any reason for calling them classical and exceptional?
Yes, so classical usually are those that come in series, and they are like just your usual matrix algebras that you just first examples. So your SLN, then you have SO2n plus 1 or SO2n, right? These are B, right? The B is SO2n plus 1, and then you have symplectic algebras. So all these are usually called classical, and they come in series, like they depend on n, and n can be any natural number, right? But there are exceptional ones, which are very interesting.
They don't have a matrix structure?
No, all algebras are matrix algebras at the end, but they are not they are not naturally introduced like that. Yeah, so for G2, for example, it has different ways to realize that. So like derivations of octonions, for example, or well, maybe we will see like in the problems for other seminar, like explicit construction of such an algebra. Yes. Okay, now we need to see that, so this one, right? So this one is alpha plus beta, right? This one is alpha plus 2 beta. This one is alpha plus 3 beta. And this one is alpha 2 alpha plus 4 beta. In any case, I needed this observation that if I have simple roots, then the angle is obtuse. The inner product is less or equal than 0 that we used in the lecture, right? For all these 4 cases, right? Well, here it's just simple roots are alpha 1 and alpha 2, right? And they, well, the inner product is 0, okay? So in this case, these are simples, right? And the angle is obtuse. In this case, so that's why I was trying to you know, write all these sums, right? This one is expressed as a sum of 2 roots. This one is expressed as a sum of 2 positive roots, right? So the simples are these 2, and I should have 2 simple roots because my E is 2-dimensional in this case, right? Rank 2. And again, obtuse angle, and here also obtuse. Yes. So we proved, finished the proof of one of the claims from the lectures. Okay. So these are the pictures. Yeah, the 5th problem is really to check that SL3 is this one. So your angles, which are given by Killing form, are exactly the ones that we have here. But actually, you can use not the Killing form, but any other non-degenerate form, like trace form, because this will be just a rescaling of this picture, right? Because SL3 is simple, and we just have essentially just one form up to rescaling. Okay, so let's stop.